All right, welcome back. I hope everybody's break was relaxing at the least, and you're refreshed and recharged. And some good news, actually, two pieces of good news. Remind me about the second piece after class. But one piece of good news is we're done with trigonometry. Yay! Rejoice. For the remainder of the year, we're going to cover a couple different topics. We are on a good pace, so we are going to spend a little time on sequences and series, and maybe possibly some probability, which I think is, very interesting and good for you guys to know. Before we touch upon our last topic, which is called limits. All right. So before we get into the probability aspect, there's a few things that lead up to it that you may be familiar with. I think you may have gone over some sequences and series in geometry, if I remember correctly. At the end of geometry, there may have been some topics along this. But just in case, geometry could have been 2 years ago for you guys. So we're going to cover it all. And, I'll take you through it. So today, we are going to talk about sequences and series. So, are we going to get to series today? Today, we may only talk about sequences. Yeah. But that's what the general topic is, sequences and series. A sequence is kind of like the name implies, a sequence of numbers. Okay, it's a list of numbers. Sometimes that list has a general pattern. Okay, sometimes it may just be kind of random numbers. So we have a few different types of sequences. Okay, a few different ways to categorize them. Like there are a few different ways to categorize triangles, right? We can name it by its sides, we can name it by its angles, we can oblique, scalene, blah, blah, blah. Right? So there's a few different ways to categorize sequences. The first way is either an infinite sequence or a finite sequence. And those definitions are pretty straightforward. And an infinite sequence is a list of numbers that goes on forever. Okay? Infinite means it never stops. Now be careful. Infinite isn't a number, right? It's more of a concept. So you can't count how many terms are in it because it keeps going on. So an infinite sequence is a function whose domain is the set of positive integers, a1, a2, a3, a4, right? So we have these little numbers there. They are called subscripts. And those are just the terms. So this is, let me get, the 1 just means that's the first term. Okay, the a2 means it's the second term. Okay, and so on and so forth. Third term. You're going to see this a lot. AN. Okay, A with a little subscript N. A sub N. We call this the nth term. Okay. Now, again, like infinity, the nth term is kind of more a concept. Okay, it's like saying, what is, instead of saying what is the 5th term, what is the 10th term, what is the 20th term, we can define a term by saying the nth term. Now, for an infinite series, an infinite sequence, it goes beyond the nth term, right? It keeps going on, and that's why all those dots are there. All right, so after a sub n, you'd have a sub n plus 1, and then n plus 2, and then n plus 3, and it would keep going on and on forever. If the function stops at the nth term, so if at some point there's no more terms, okay, then we call it a finite sequence. Right, so that's one way we can categorize a sequence. Is it infinite? Does it go on forever? Or is it finite? Does it have a beginning and an end? All right. Now, there are two ways we can represent sequences. Okay, the first one is called explicitly. An explicit definition or an explicit function okay, when you see an explicit function, it tells us directly how to find the nth term. Right, so for an example down here, I have this explicit function a sub n equals 3n minus 2. And I want to find the first four terms. All right, so let's write that out. So the first four terms, okay, would be a1, a2, a3, and a4, right? First term, second term, third term, fourth term. To find them, I'm going to plug the n, whatever little number I have here, that's what goes into the formula. Oops, minus 2. Right? So 3 minus 2 is 1. That is my first term. It's just a coincidence that a1 is 1. You won't always have that, okay? But again, what this tells me is I'm plugging in this 1 into where the n is. Okay, a sub 2, I'm going to plug in 2. Oops. So that is 6 minus 2. So my second term is 4. My a sub 3, I plug in 3. That's 9. 9 minus 2 is 7. And then my fourth term is 3 times 4 minus 2. So that is 12 minus 2, which is 10. So here I have my first four terms of the sequence. 1, 4, 7, and 10. Now you may notice the pattern to get from term to term. Right? It's from here to here, from here to here, from here to here. And you may see that that pattern appears in your expression. Right? So what's the common thing that as I go from one term to the other? What's another way I can say how to get from one term to another? What do you see as the pattern? What do I do from 1 to 2, from 2 to 3, from 3 to 4? Anybody? What's a common?
Repeat the question again.
Not looking at this. Just if you just had the numbers 1, 4, 7, 10, and you were told that they were in a sequence, how would you get from one term to another? What's the pattern to continue on?
Adding 3.
Add 3, right? Plus 3. Plus 3. So if I wanted to keep going, I could keep adding 3. Well, look at what we're multiplying by, right? So you can kind of start to see those relationships between the explicit function and what's happening with our sequence. Okay, any questions so far? I know some of this might be new with the a sub n, with the an, but really it's just patterns. So any questions so far? Okay. So using that, Okay, so again, just a little clarification, right? So if you see explicit, the formula or the function tells you what term you're looking for. Okay, so again, if you had a sub 5, that tells you that your n is 5, and you would plug in 5 to the explicit formula, right? So what's nice about this is I can find any term that I want. If I wanted to find the 101st term, right? It would take me a while if I started with 1 and did plus 3, plus 3, plus 3, and I had to do that 100 times. But with this, I can just plug in 100, and that would be 300 minus 2, so I know the 100th term is 298. Okay, so that's what's nice about the explicit form. But we can also define a sequence using the pattern. Okay, there we would say that a function can be defined recursively. So having a recursive function means that we find the next term using the previous term. Now, there's a childhood example of this that you may not be aware of. Is anybody familiar with the Fibonacci's number, with Fibonacci sequence? Does that ring a bell for anybody? Fibonacci. I'll take that as a no. Okay. Well, so before I get into that, then let me talk about this. So here, our names are a little different, the way we have the function. So here I used k instead of n, but it means the same thing. So here, this is saying a sub k is equal to a sub k minus 1 plus 4. So this is saying to find the new term, we take the previous one and add 4 to it. Okay? So, if I wanted to find a 10, well, that would be a 10 minus 1 plus 4. So that'd be a 9 plus 4. Right? So to find a 10, I would need a 9. Okay? So to find a 9, I would need a 8. And then I would need a 7 and a 6, 5, 4, 3, 2, 1. Okay? So for recursive, you need at least the first term to find the rest. You can't start from nothing. Another way you might see it, the new term might be n plus 1 or k plus 1. And then the previous term, would just be a sub k or a sub n. All right, so let me I don't want to do this. Okay, yeah, let's. So the Fibonacci sequence is an interesting set of numbers that this dude Fibonacci came up with a long time ago. Okay, and it goes on forever. Okay, it's 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and it goes on forever. Now, this is a sequence. What's interesting about this is it's really difficult to find an explicit sequence for this. Okay, there's no way I can say that an equals whatever. But the rule for Fibonacci, to find a new term, I take the previous two terms and I add them up. So if I wanted to find the 9th term, I would need to add 9 minus 1, the 8th term, plus 9 minus 2, the 7th term. Right? So actually, technically, it starts with 0. You have 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And it goes on. 8 and 13 is 21. I think I did my math right. So if I added wrong, I apologize. 13 and 21 is 34. 21, 34 is 55. And it goes on forever. Okay. So again, this one is only able to, we are only able to define this using a recursive formula. Now, I bring up Fibonacci sequence because it's a really interesting set of numbers. And it actually gives us a lot of things in real life. If we divide all the numbers in order, so at the beginning, it's kind of, you have 0 divided by 1. So this is going to be a side lesson. We get 0. 1 divided by 1, we get 1. 2 divided by 1, we get 2. But when we start getting up to the higher ones, 3 divided by 2 is 1.5. 5 divided by 3 gets us 1.6 repeating. 8 divided by 5 gets us, I think it's 1.6 even. Yeah. 0.6. 13 divided by 8. 1.625. And then we do 21 divided by 13. 1.615. And I'll do one more. 34 divided by 21. We can see as we divide these numbers, this one should actually, we're not going to use that one. The resulting ratio kind of hones in on a number. What we call that is the golden ratio. And let me get the exact value. Okay, so we were pretty close here. The golden ratio is approximately 1.61803398875. This number appears a lot in just everyday nature. The proportion of your limbs, I think it's your finger to your hand to your, from your wrist to your elbow, the ratio between the size of your ears and your face. If you did these calculations, a lot of those numbers, a lot of those ratios would be around here, 1.618. In actual nature, it's found a lot. For those of you who are art majors, you may be aware of the golden ratio through something called, where is it? The golden spiral, which is kind of a way that things look nice. Let me change this so you guys can see the picture. It's not presenting. Present. Let's present the screen. Okay, so here on the right and over on the left a few different times, we can see what we do is we construct squares with areas that are equal to the Fibonacci sequence. So the first two squares have an area of 1, then it has area 2, then 3, then 5, then 8, then 13, and it keeps going. And we keep adding these squares on, and we create this spiral that touches each one of the squares, and this is known as the golden spiral. Now, this is used in art a lot, okay? You can superimpose this spiral on a lot of famous photographs, famous paintings, and it's just kind of the aesthetics of the picture. You know, it's pleasing because it's a natural occurring phenomenon. All right, so here you have what is this picture? Oh boy, I wish I paid attention in art history in college. This is a famous Japanese picture of, you know, the wave. Here you have the girl with the golden earring. Okay, this one's kind of a rough fit, but you can see how the golden spiral takes place. In Mona Lisa, it kind of fits here. So for those of you, you know, in art, in things like that, okay, this appears quite often. Even just the proportions of the different sizes. Okay, it also appears a lot naturally in nature. The formation of sunflower seeds being, you know, sprouted in the middle of a sunflower. It follows this pattern. The first inner circle, the outer, and then the circles, you know, resulting from that. Nautilus shells and, you know, seashells naturally form using the golden ratio. Okay, if you superimpose the golden ratio over this, it would fit perfectly. Flowers, okay, roses, certain types of plants like cauliflowers and cabbages kind of follow this spiral pattern. And this is, you know, completely unaided by the human hand, right? If you just planted some of these things out in nature, more often than not, they would find this pattern. And then even going to the extreme, okay, the shape of the galaxy, the Milky Way galaxy that we are in, the shape of tornadoes and hurricanes, they all kind of fit nicely into this golden spiral. I don't know what this ad is over here. I apologize for that. I got to be careful what I click on. Stop. All right. And you know, this is just the resulting of some guy adding numbers together, right? 0 and 1, 1 plus 1, 1 plus 2, 2 plus 3, and continuing on like that. So I wanted to take a little side track there just to kind of introduce you to that, because that's something I think is super interesting, and you know, it's a great way for people who are always like, oh, what does this have to do with real life? Well, you know, look at right there, I just showed you, you know, through man-made art and through actual physical nature, right? These things appear naturally. All right, and you can do your own research with that. I'm not going to get too much deeper into the golden ratio and the golden spiral and Fibonacci. I just thought it was a good way to start to introduce this. All right.